I'm Claire. Today let's talk about a problem about we know we have a two-dimension Euclid geometric, right? We have Euclid geometric in 2 dimensions, of course, in 3 dimensions. So we think about it in a 3 dimension. We know in a 2 dimension that a triangle satisfies so A plus B greater than C all the time. So we're just gonna check in this video is to think about this case, a triangle in a ball in the 3 dimension. You can think about a ball, right? On the surface of the ball. On the surface of the ball, right? Now let's think about. First, we know, for example, we will have a line. For example, we have A, B. And if we choose the closest line from A to B, we have to think about the geodesic line, and we're going to think about we have a geodesic circle over here. It is point A, point B, and the circle center create this circle. And the circle center, we just set it at O. Okay, so we know we have the superior arc and the minor arc. So we choose the minor arc and not the superior arc because the superior arc is longer. You see, if A, B, then their superior arc from the geodesic circle is this part, right? This part. But this line, this arc is longer than the minor arc. So we have to choose the minor arc. We cannot choose the superior arc. Okay, we just think about a geodesic circle here. Okay, created by A, B, and O. Okay, O is the circle center, remember. Here, now let's think about A, B, and C. So we create this triangle. Be careful. This is 90 degrees, this is 90 degrees, and this is also 90 degrees. Okay, now let's just think about a problem. We think about that, we just think about, because if A plus B plus C is gonna be greater than C, A plus B is gonna be greater than C, then we can just think about the situations about that A plus B equal to C, or A plus B less than C. Okay, so this situation must satisfy. Okay, now let's calculate. And this length, this arc is what? It is pi r over 2. Because the whole circle, the whole arc of the circle, it is what? It is 2 pi r. We divide 4. So this length, this arc, it is pi r over 2, and this is also pi r over 2, and this is also pi r over 2. Okay, so pi r over 2 plus pi r over 2 equals 2 pi r over 2 greater than pi r over 2. Okay, now let's think about it. We can move A and B. So A and B are over here right now. Then we can move A. We don't move B, and we move A here. And so A and B are these points, and they are on these 2 points, and C is at the pole point, at one of the poles. Okay. You can say it's at the North Pole, maybe it's North Pole, whatever. We just call it. This is a pole point, and now this situation. So C, A, C, B, they're still, because they're actually the paddles. They're the meridians. They're the meridians. Okay. They're actually the meridians, right? Okay. This line and this line are the meridians, and they are always, in this case, they're always pi r over 2. And you can just think about AB is over here, and AB, we choose this minor line, minor arc, it's over here. Okay. Or it's over here, that's fine. Because now A and B are just these 2 points, so these two lengths are the same. They're both pi r. So we just think about this one. And this is pi r, and this is pi r over 2, and pi r over 2. So this satisfies that AB equals C. Now let's think about the problem over here is this does not satisfy in the definition of the 3-dimensional triangle in the Euclid in the Euclid geometric. Let's just think about it. So this what became this first we think about in this case we can draw because C to A and C to B and A to B they have 3 geodesic circle, and CA we have this geodesic circle, and CB we have this geodesic circle, and AB had this geodesic circle. So remember, we didn't actually have to say because AB are on these 2 top points. Then what? Then we have infinite geodesic circle because we get this one. Okay, and we can choose this one, and so the 3 geodesic circle are at the same one. They are superposition. They are the same circle now. Okay, so here's the point. Now let's move. I'll tell you another question. You will think about this right now, but I'll tell you later. Here's the case 1. Now we move AB. We can just watch it like this. So this is A, and this is B, and this is C. Now we can move A a little bit here and B a little bit there. Actually, you just move any of them just a little bit. And then C cannot be here because A and B and O, ABO, they create a geodesic circle. Now it's only over here. They cannot change because it's different. A and B are over here, but now it's A and B are over here. Then the geodesic circle only can be here. Okay. Then C, in an instant, it will change over here. Well, actually, because A is over here and B is over here, in the middle of A and B, everywhere, it can exist. Now let's think. Oh, so it satisfies what we say. Oh, now CA, for example, C is here, and CA, CB, and AB, they're at the same circle. So we cannot actually create a what? An area on the sphere of this ball because they're at the same circle, and this become a line. Right. And now we can see. And then we move AB closer and closer to here, and actually it's everywhere we can move it over here. And we move, for example, we move to here. What do we happen? And then because A, B, C, they're like this. This is C. This finger is C, and this middle finger is B, and this thumb is A. Now look. Now they are in a delta, or can say epsilon range or domain. They staying here. We cannot see, but exist. And this is like that we collapse from 3-dimension to 2-dimension. And now we think about a 2-dimension. Okay. Right, and here's the point. Now think about it. This is the case 1. So finally, just collapse to 2-dimension. Okay, now what's the point? We have a case 2. We ask when A and B, we just look at this, right? A and B are over here, and C are over here. And we think about, oh, now I have a question. Because I say that AB can be here, and also can be here. We say that AB over here, so how can we just explain this? We can say A and B. Now what we choose is this geodesic circle created by A, B, and O is perpendicular with C and A and C and B geodesic circle. Now they're perpendicular. We think about, oh, we have a situation. Now you say, oh, then A is over here, C is over here, B is over here. Then we have this line and this line. Oh, now I create an area on a sphere. Okay, I have this area. Now let's think. How can we calculate this area. Now, let's just have a look. We're gonna calculate this area, and so first, the whole area of the sphere of the ball. We'll talk about some video after, and this is 4 pi r square. Okay, now because this part for the angle, because we look like this, right? If we look like this, then it looks like, because one of this over here, and this we can figure a half circle. I'm sorry. This a half circle is over here, and another a half circle is over here, and then we are just think about because the half circle is over here and over here, and we just gonna think the whole circle, and we can think the angle over here. And this is a 360 degree, and then here it is 90 degree because we set it as perpendicular. So right now we have to times what? We have to times 90 degree over 360 degree. Okay. That's great. Now, if we have this, then if we calculate this out, because this is 4, so this is equal to pi r squared. So usually we have a area over here. And you ask, why? Because this become a diagonal. This is a diagonal. Because from C to A and C to B, it's becomes, because here, we're going to think about it, because if we think about it as a triangle, here is 180 degree, and here is 90 degree, and here it is 90 degree. And so here it is 180 degree. So that means CA to CB is like it is on the same circle, right? It is on the same geodesic circle. So it just looks like a one arc. Right, and this arc, so it becomes a diagonal. We can imagine. Okay, we only have A and B. Okay, now we have a diagonal. That's what we call degeneration. We degenerate. It is a degenerate case for this. For case 1, of course, Okay, of course here, in this case, right now, so A and B. Now, if we look like this. Now, A and B, we just move it a little bit and become case 1, what we talk about. Okay, see, and then this, in an instant, we move to here, and then blah, 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 blah. Okay, and just move to some kind of an epsilon constant, but it just become a collapse from 3 dimension to 2 dimension, just like this. Okay, just in the case 1, we say about it. Okay, now the point is, now becomes, and case 1 degeneration is because they become at the same geodesic line. And this case is that it turns to a diagonal. So it also degeneration. It's also degenerate. It's also a degenerate case. Degeneration case. All right. So this is what we actually think about. All right. So we always say, okay, A plus B equals C is a degeneration case. That's wrong. And A plus B less than C, only one case. Because right now we think about the minor arc. And we can think about the superior arc. And the superior arc, for example, A and B is over here. Now we move it a little bit over there, and we can choose the superior arc and not the minor arc. So to here. All right, and this line, and with C, for example, just move. C doesn't change, and move to A and move to B because this is a meridian. So that is did not change. It's still pi r over 2. Pi over 2, so plus together takes pi r. So pi r is only start from here to here. But now it is start from here to here. So it's going to be longer. So this is by this. But now we just, because the definition is not to choose, we have to choose the meridian meridian arc and not the superior arc. So this is also wrong. Right. Okay. Now there's just something else, because if we always think about CA, CB, and put them together, that's always greater than AB. We're going to think about some kind of, I just say that as a, because so first we can do the dot product with C and A. So this means, and so for example, the first symbol to talk about here's A, here's B, and here's C. What we do is AOC. So this means measure the angle, then time, if we calculate this theta, and we can just times the radius. And then we set the radius 1, so just measure to this arc, and we're going to say the degree, right? So 90 degree plus CB measured to 90 degree and equals AB, AOB, that's 180 degree. Right. So we just measure like this, right? Okay. Yeah, that's right. Yeah, okay. Yeah. So now let's think about C times A. So if we have 2, because we just set the R radius is equal to 1. Okay, you can see that, right? And so we can set C is over here. Okay. Okay, now this is A and this is vector C, and we have 2 vectors and we do dot product, so we have, okay, and this is the mod of C and times cosine theta, so we set this angle as theta, and times, okay, and this is A, vector A, okay, and calculate its mod right now. Alright, at this, then, okay, so we count cosine theta and R equals 1, so this and this guy are equal to 1, so now we just arc cosine. It's very easy. Cosine, arc cosine. Okay, and this measures the CA. Okay, see this, can you? Plus arc C times B. This measures the CB. And then, that's greater than arc C, A, dot product B. Not C times B, it's dot product, sorry. And that's A, B. Sorry. Okay. Now today's video is finished, and this video is what we talk about this A plus B greater than C. In the definition that you calculate a geometric, it's still satisfying the 3 dimension. Okay, so this is today's video.